Welcome, my dear learners, for this course on control engineering. From today, we are beginning a new module, that is in module 4, we will be discussing on root locus. What is this root locus? Why we are studying this in control engineering? Let me explain this properly. In our previous module, that is in module 3 itself, we have studied transient and steady state responses, wherein which we have conducted stability analysis. What do you mean by stability analysis? The analysis of a control system to know whether the system reaches steady state after passing through the transient state. As you all know, the system response of a control system has two solutions. One is transient part and another one is steady state part. So the total system response is containing both transient as well as steady part. Let me give an example of an air conditioning system to understand what you mean by stability analysis. In a room, if I want to attain around 20 degrees Celsius, whereas the atmospheric temperature is around 28 degrees Celsius, what I will do, I will switch on the room air conditioner and set the temperature to 20 degrees Celsius. Initially, the temperature will be the temperature what is there inside the room before switching on to the air conditioner. Then the air conditioner slowly picks up and reaches the temperature around 20 degrees Celsius, which might be not exactly equal to 20 degrees Celsius. So what I mean to say is that the system response or the response of a room air conditioner, here the response what I require is nothing but temperature. Here X is nothing but what? Temperature. What is the value of temperature I require? 20 degrees Celsius. Let us assume the temperature of surrounding is something else and it is coming to reach 20 degrees Celsius. How it will reach? It will take some time, correct? It don't suddenly come and reach 20 degrees Celsius. The room air conditioner will take some time, after which it will reaches nearly equal to 20 degrees Celsius. It might be 19.8 or 19.9 or 20.1, like that. Now after reaching, once it reaches nearly equal to 20 degrees Celsius, then it will stay at 20 degrees Celsius itself. So this is called as transient part. This is called as transient part, where it was struggling to reach 20 degrees Celsius, the room air conditioner, and once it reaches the value nearer to the 20 degrees Celsius, it attains steady state part. Steady state part. So stability analysis is nothing but analyzing the system whether it reaches the steady state after successfully passing through the transient state. And this minute difference between the desired value and the actual output is known as steady state error. Is called what? Steady state error. Now the stability of any closed loop control system can be determined by plotting poles in a complex plane. Why we are plotting it in a complex plane? The poles are complex in nature. It has both real part as well as imaginary part. So therefore the stability of a control system can be analyzed. Stability of the closed loop control system can be analyzed by plotting closed loop poles in complex plane. In complex plane. So this complex plane is also called as what? S plane. The another name of complex plane is S plane. Simply we call it as S plane or complex plane. Now the closed loop poles are nothing but what? The closed loop poles are nothing but roots of the characteristic equation, correct? So the closed loop poles are nothing but roots of the characteristic equation. The closed loop poles are nothing but characteristic equation. Roots of the characteristic equation, that is roots of the characteristic equation is given by 1 plus g of s into h of s is equal to 0. The roots of this characteristic equation are nothing but closed loop poles. By locating the closed loop poles in a complex plane, I can determine the stability of a closed loop control system. The very important part to be noted down here is the transient part. If transient part is too much, what I mean to say is that time required to successfully complete the transient part is too much for a control system, then the system is relatively less stable. If this transient part is very small and system reaches the steady state quickly, then the system is said to be more stable. Now, as I said, the system response is nothing but the output of a system as a function of time. As I said, the system response x of t has two parts, that is x transient plus x steady state. Steady state, you don't worry, steady state is a constant value. I don't want to worry about that. What about this transient part? If you observe, transient part is varying. This transient part varies exponentially. The transient part of a system output varies exponentially, which I can write it as a constant into e to the power of ut. A constant into e to the power of ut is the system response for a transient part. Now, as you observe, the transient part varies exponential as a function of ut, where a is constant, u is the root of characteristic equation or closed loop pole. So, what is u here? So, a is constant, whereas u is pole or root of characteristic equation. Now, a careful observation will reveal that if the value of u is negative, if the value of u is negative, what happens? As the time increases, as time reaches to infinity, this will vanishes and the system reaches the steady state quickly. If the value of u is positive, what is going to happen? It will exponentially increases. The transient is very high in the system. What I mean to say is that if u is positive, then transient response is very high. If u is negative, then transient response decreases as increase in time. That is, if I plot the poles, the value of u in a plane like this, if I plot the value of u in a plane like this, that is closed loop poles, let us say I have a pole here, let us call it as u1. So, for u1, if you carefully observe, u1 is a negative value, if I substitute negative value here, what happens? As time increases, the transient part will vanishes as time tends to infinity. So, this is called as S plane. This is real axis and this is imaginary axis. This is nothing but complex plane or S plane. Complex plane or S plane. So, in a S plane, if the pole is located to the left half, so this is left half and this is right half. This is right half. If the pole is located towards left half, then the root is negative. This is positive, right? This is negative x-axis. This is positive y-axis. This is negative y-axis. The root is real and it is negative. So, therefore, what happens to the system response? The system will reaches steady state as time increases, correct? Like this. As time increases, the system reaches steady state. Time. So, I am plotting only transient response, which is a function of time. Now in order to avoid confusion, let me use transient as capital T. Capital T stands for transient, small t stands for time. This is transient. Contrary to which, if the root lies on the positive real axis, that is towards the positive side, what happens? What happens in that case? This is real axis and this is imaginary axis. Let the root lies in the positive real axis. Let us say the root lies here. This is the value of u. Since u is positive, what happens to the transient response? It increases exponentially. So what is the output that I am going to get in a transient output? It is very, very unstable. Like this, I will get the system response. Correct? It is not at all reaching the stability. If t reaches the value of infinity, the transient part reaches the value of e to the power of infinity. Exponential of infinity it will reach. So the transient is too much. This is absolutely unstable. This is what? Unstable. What about this? This is absolutely stable. This is absolutely stable. So what is your observation from this? So if I plot the graph in S plane, S plane is nothing but the complex plane. S plane is another name of complex plane, in which we have both real axis and imaginary axis. So what is our interpretation from this? If the closed loop poles lie towards the right half of the plane, the system is said to be unstable. If the closed loop poles lies towards the left half of the plane, then the system is said to be stable. For a system, control system to be stable, the poles should lie in the left half of the imaginary, left half of the S plane. If the closed loop poles lies towards the right half of the S plane, then the system is unstable. So stability condition is that the poles should lie on the left half of the S plane or a complex plane. S plane is a synonym for complex plane. So this is what the stability analysis is. Now how it is related for root locus is the question, right? Why I am explaining this stability analysis in root locus, you might be wondering. Let me connect why I am explaining these things to root locus. Hope the concept is clear till this point what I have explained. Now moving further, we have another parameter called relative stability. We have another parameter called relative stability. So relative stability, a system is said to be relatively stable if the time required for the setting time is lesser. That is, if the transient time is less, then the system is said to be more stable. If the transient part is more, then the system is said to be less stable. If the transient part is very high like this, in this case the system is said to be unstable. So a system is said to be relatively stable if the setting time is less. So therefore relative stability is defined based on what? Setting time. Setting time is a time which is required for a control system to reach the steady state after passing through the transient state successfully. Now this setting time is inversely proportional to real part of closed loop pole. It is inversely proportional to real part of closed loop poles. It is inversely proportional to closed loop poles. So what you interpret from that? If the closed loop pole is increasing or it is moving towards the infinity, then the settling time will become very, very small because it is inversely proportional to closed loop pole. As the closed loop pole value is keep on increasing, the settling time will keep on decreasing provided the pole lies in the left half of the S plane. So therefore the system will be more and more stable if this pole moves towards the minus infinity. If this pole moves towards the minus infinity. So this is connected to root locus. Now as I said, the setting time is inversely proportional to closed loop poles, which means that if poles moves towards minus infinity, the system will be more and more stable, relatively more and more stable. Now I want to observe what is the effect of some parameter on the closed loop control system and how the stability is affected because of the small variation of the parameter. Hence the root locus is defined as a small variation in a parameter in a closed loop control system will affect the roots of the characteristic equation. Correct. So if I change a parameter in a closed loop system, the equation 1 plus g of s into h of s is equal to 0 will be changed. So therefore the roots of this equation will also change. If the roots of this equation is changed, then closed loop poles will also change. If I plot the closed loop pole, I should ensure that it will always lies towards the left half of the S plane, and I am desired to obtain the closed loop pole such a way that it is moving towards the minus infinity. Correct. So a change in a parameter in a closed loop system will change the characteristic equation, which will change the closed loop pole. So if I keep on changing the parameter in a closed loop system, it will keep on changing the poles. For every value of that parameter, I will get a new value of pole. I will keep plotting them and connect those things, which is nothing but I will obtain a line. That line is nothing but a locus which is obtained for a poles, which is known as root locus. So to know what is the effect of change in parameter in a closed loop control system, we use root locus method, which was suggested by Evans in 1948. In 1948, a scientist named Evans demonstrated how to study the variation of small parameters in a closed loop system will affect the stability of a system, was given by a closed root locus method suggested by Evans in 1948. So therefore, what is the meaning of root locus is the question. As Evans suggested, a small variation in a variable parameter in a closed loop control system will vary the output, that is vary the characteristic equation. If this characteristic equation is varied, the closed loop poles will also vary. So this closed loop poles should vary such a way that it should come on left half of the complex plane when I plot it. Then only the system will be stable, otherwise the system will be unstable. This can be understood by a method called root locus method. Now let us consider a root locus. Now I came to the point. Root locus. Let us consider a closed loop system like this. Let us introduce a new parameter k to the system which has g dash of s giving an output. Let us have a feedback h of s like this to the system. Now if I write the characteristic equation of the system, what I am going to get? 1 plus k times g dash of s into h of s is equal to 0 is the characteristic equation of this closed loop control system. Let us have an input r of s and output c of s. Now if I vary the value of k, I will get the different values of roots of this characteristic equation, which means that I will get different values of poles. If I plot these poles on a complex plane or S plane and connect those poles, I will get a locus. Locus means nothing but a line. That line is called as root locus, which is nothing but the root of the characteristic equation. The locus obtained by plotting the roots of the characteristic equation for various values of k. What is k? K is a variable parameter. I am varying a parameter in a control system, and I am studying how the system is responding for that variation, whether it is becoming unstable or it is becoming stable. This can be analyzed by plotting root locus. So therefore, I am interested to study how the poles, closed loop poles, move in the S plane. So if I vary the parameter k from minus infinity to plus infinity and plot the closed loop poles, which are nothing but roots of this equation, characteristic equation, and connect these poles, I will get a locus poles. We will get a locus which is nothing but root locus. Locus is nothing but a line on which the root of the characteristic equation will come and lie. What is that giving us? So if I determine the root locus, I can observe on that line how the poles are moving, whether the poles are moving towards minus infinity or the poles are moving towards plus infinity, which means that whether the system is moving towards the stability or the system moving towards the instability is the point of interest, which can be determined by graphical method suggested by Evans, that is nothing but root locus technique. Hope the concept is clear. Here we are studying the effect of a variable parameter on a closed loop control system. What is that effect? Whether it is making the system stable or unstable, which we can analyze graphically, suggested by Evans, which is nothing but root locus method. Let me pause this video for a while so that you people can copy down the concept of stability and relative stability. Why people say that if the roots of a characteristic equation lies towards right half of the S plane, the system is unstable, and left out of the S plane, the system is stable. This is the reason. So this is the concept of stability. So based on stability analysis and the relative stability concept, we understood what is the meaning of root locus. So let me pause this video for a while. Later I will take up what are the conditions we are going to get from the root locus, and I will demonstrate this explanation what I gave with a graphical representation. Now moving ahead, as I said, the root locus is nothing but the study of effect of variation of a variable parameter on the system by graphical method. We will determine the characteristic equation, its roots, which are nothing but closed loop poles. We will plot that poles and check whether the poles are moving towards left of the S plane and making the system stable, or they are lying on the right half of the S plane and making the system unstable. Now the characteristic equation what I wrote is k g dash of s h of s is equal to 0. Let me call this as g of s. G of s is nothing but the product of k times g dash of s is the characteristic equation, right? Now I want to vary the value of k and see the movement of poles. If I join those poles, I will get a straight line. I will get a line, and that line is nothing but root locus. If I vary the value of k, from 0 to plus infinity, then the line obtained by joining the poles is called as direct root locus. Is called as what? Direct root locus. If I vary the value of k from minus infinity to 0, and solve this characteristic equation and obtain the n number of poles, connect them, I'll get the root locus, which is called as inverse root locus, which is called as inverse root locus. Unless otherwise specified, always will solve for direct root locus. Keep that in mind. Always will solve for direct root locus. Now let us plot a root locus and understand the meaning of root locus more better. Let us take the question like this: plot the root locus for the unity feedback system, for the unit feedback system with g of s is equal to k by s. Take down this question. Plot the root locus for the unity feedback system with g of s is equal to k by s. So we have the value of g of s. So I said it is a unity feedback system, therefore h of s should be equal to 1, correct? So what is the solution? H of s is equal to 1 and g of s is k by s, so therefore characteristic equation will become what? Characteristic equation, that is 1 plus g of s into h of s is equal to 0, which means that 1 plus k by s must be equal to 0. K by s into 1 is k by s, that is s plus k is equal to 0. Therefore what is the value of s? S is equal to minus k. Now plot the values of s in the complex plane or s plane. Now vary the value of k. So for various values of k, if k is varied from 0 to plus infinity, varying k from 0 to plus infinity and plot it, what are you going to get? If I plot it, what are you going to get? So this is imaginary axis and this is real axis. If k is equal to 0, I will get a pole here. If k is equal to 1, I will get s is equal to minus 1 somewhere here. If I put s is equal to, k is equal to 100, I will get s is equal to minus 100. So if I put like that, if I keep increasing the value of k, s will become negative of that. So the system is moving towards stability, correct? Like this the system is moving, correct? So therefore what is the root locus? The root locus is nothing but, yes, what is the root locus? The root locus is nothing but negative real axis. Therefore the root locus is negative real axis. Negative real axis of S plane or complex plane. So what is the solution for this problem? The root locus is the complete negative real axis, that is towards the left half of the S plane. Hope what is the meaning of root locus and why we are studying root locus is clear now. Now with the help of the characteristic equation and the concept of root locus, we can obtain two conditions. That is, one is called magnitude condition, another one is called angle condition. What is this magnitude condition and angle condition? Let me explain. Now we have the characteristic equation, that is magnitude and angle conditions. magnitude and angle conditions. The characteristic equation is given by what? 1 plus g of s into h of s is equal to 0. So therefore, what is the value of g of s into h of s? G of s into h of s is equal to minus 1. Always remember, what we are plotting, the graph is a complex one. It is a complex plane, which is a S plane is a complex plane which has both real part as well as imaginary part. So therefore, I can write this as g of s into h of s is equal to minus 1 plus 0j, 0 imaginary part. Minus 1 is the real part, 0 is the imaginary part. I can write it like this. Correct? From this I can get the angle condition and magnitude condition. What is the magnitude condition? Magnitude condition is that the modulus of g of s into h of s must be equal to modulus of this. What is the modulus of this? It is plus 1. So the value for any value of s given to lie on a root locus, the modulus of g of s and h of s must be equal to unity. If this condition is satisfied, then the given value of s will lie on the root locus point. So this is the first condition. Now coming for angle condition, second one. Angle condition. The angle condition can be obtained by taking angle on both sides. So in which form we have? This is of the form rectangular form, right? So this is rectangular form. Now in order to obtain the angle condition, we have g of s into h of s is equal to minus 1 plus 0j. Now convert this into polar form. This is in rectangular form. This is rectangular form. Now taking polar form, that is polar of g of s h of s is equal to polar form of minus 1 plus 0j. So therefore, what is the angle condition you are going to get? How to get the polar form? So using calculator, I think you people have forgotten. Let me come to you and explain how to get the polar form. See, there we have the rectangular form as minus 1 plus 0j, correct? So therefore, what I should do? I should go for shift polar form. You can see here POL, pole. So shift polar form I want. Polar form I want. Inside that you should type rectangular form. What is the rectangular form? There you have the value minus 1 plus 0j. That I can enter as minus 1 comma, you should write always, keep that in mind, shift comma. What is the value of imaginary part? 0. So close this. If I press equal to, I will get the magnitude as 1, that is correct. What is the magnitude condition? Unity. And what is the value of angle theta? 180 degree. Hope that is clear. Whenever you want polar form, go for shift plus polar form. Inside the bracket, enter the rectangular form using comma. First one is real part, comma, second one is imaginary part. Press equal to, you will get the magnitude and angle. Magnitude is unity, correct? Magnitude condition is unity and angle is 180 degree. So therefore, g of s into h of s should be equal to plus or minus odd multiples of 180 degree. Keep that in mind. It should be equal to plus or minus odd multiples of 180. Odd multiples can be written as 2q plus 1 into 180 degrees. 180 degrees. Now put q is equal to 0. I'll get 0 plus 1 as 1. 1 into 180 is plus or minus 180 degree. That is what I have shown you. Now put q is equal to 2. Put q is equal to 2 and check what you will get. 2 to the 4. 4 plus 1 is 5. 5 into 180 degree. Put q is equal to 1. You will get 2 plus 1 is 3. 3 into 180 degree. So like that, if you get the angles, that is odd multiples of 180 degree, then the angle condition is satisfied. That is, you should get, what is the angle condition says? You should get odd multiples of 180. Odd multiples of 180 degree. So hope you understood how to convert from rectangular form to polar form. So if these two conditions are satisfied, then obviously the given value of S will lie on the root locus. That is nothing but the pole will be on root locus. Now in order to understand this magnitude and angle condition better, let me take an example. Check whether S is equal to minus 0.75 lies on root locus for G of S into H of S is equal to K divided by S of S plus 2, S plus 4. Take the problem. Take the second example problem. Check whether S is equal to minus 0.75. S is equal to minus 0.75 lies on the root locus for G of S into H of S is equal to K divided by S of S plus 2 into S plus 4. Now in order to check whether S is equal to minus 0.75 lies on the root locus, I can use the conditions what we have, angle condition and magnitude condition. Since I don't know the value of K, let me calculate the value of K by using magnitude condition. If I go for magnitude condition, I can determine what is the value of K. That is, modulus of G of S into H of S must be equal to 1. Correct? Now if I go for magnitude condition to find the value of K, that is modulus of G of S into H of S at S is equal to 1 must be the answer. Correct? So therefore modulus of K divided by modulus of minus 0.75 modulus of minus 0.75 plus 2 into modulus of minus 0.75 plus 4. This must be equal to unity. Right? So therefore what I will get? K divided by 0.75. So modulus of minus 0.75 is 0.75 into 2 minus 0.75 is 1.25. Modulus of 1.25 is 1.25 into 4 minus 0.75, that is 3.25. Modulus of 3.25 is 3.25 itself. This must be equal to unity. Hence if I solve, I will get the value of K as K will become 0.75 into 1.25 into 3.25. That is, the value of K is turning out to be 3.0468 So I got the value of K. K is 3.046875. Now using magnitude condition, I got the value of K, which is not given for us. That is the variable parameter K I obtained. Now for the value of K is equal to 3.046875, whether S is equal to minus 0.75 lies on the root locus or not is the question. Now in order to check that, let me use angle condition and check whether I will get the odd multiples of plus or minus 180 degree or not. Now move for angle condition. Angle condition states that angle of G of S into H of S must be equal to plus or minus 2q plus 1 into 180 degree, where q can take a value of 0, 1, 2, 3, etc. to infinity. That is odd multiples of 180 degree. Here the q can take any value from 0 to infinity. Now to obtain the angle, this is in rectangular form, but I can get the angle in polar form. Just now I demonstrated how to get the polar form from rectangular form. Let me write that once again. That is the angle of K divided by angle of S is minus 0.75 into angle of S plus 2. S plus 2 is 1.25 into angle of S plus 4 is 3.25. This is what we have. Now what is the value of K? K is also known for us. K is 3.047. Let me put it as 3.047. Now all these values are real. That does not contain imaginary part. Correct? That does not contain imaginary part. So therefore I can write this as what? Angle of 3.047 plus 0j divided by angle of minus 0.75 plus 0j into angle of 1.25 plus 0j into angle of 3.25 plus 0j. Because we are solving for complex plane, this should be complex numbers. So this is in rectangular form. I should convert this into polar form. So the polar form of answer will be how much? Just I want to take the angles. I don't want the magnitude. That is let me take the first one, 3.047 plus 0j. If I take the first one, so first I should press shift polar form of 3.047 plus 0j. That should be entered with comma 0, bracket close. How much? I don't want magnitude, I want only angle. Angle is how much? 0 degrees. Note down, 0 degrees for first one, numerator. Coming for denominator, it is polar of shift polar of minus 0.75 comma 0. How much? Angle is 180 degree. Next is 0.25. How much angle? 0. Next last one is 3.25. How much is the angle? 0. So what are the angles we got? 0 degrees divided by 180 degrees, 0 degrees, 0 degrees. Now how to solve this? Numerator angles are taken as positive, denominator angles are taken as negative. So therefore the angle will be 0 minus 180 minus 0 minus 0, which is nothing but minus 180 degree. So numerator angles are taken as positive, denominator angles are taken as negative, and solve like this: 0 degree minus 180 minus 0 minus 0. So answer is minus 180 degree. Minus 180 degree is nothing but the angle condition. Since it is satisfying angle condition, therefore S is equal to minus 0.75 lies on root locus. So therefore S is equal to minus 0.75 lies on root locus. This is because of the reason it is satisfying the angle condition. Now using magnitude condition I got the unknown k. Using angle condition I verified that it is lying on the root locus. Hence this is one of the pole, which means that if this is one of the pole, what does it mean? It is a root of characteristic equation. So this is minus 0.75 is a closed loop pole, which means that it is a root of characteristic equation. So the characteristic equation 1 plus g of s into h of s is equal to 0. The characteristic equation what we will get for that characteristic equation minus 0.75 is one of the roots. Then only it will become a closed loop pole. So then closed loop poles can only come and lie on root locus. So therefore using the root locus technique I can determine the roots of higher order polynomial equations. So therefore using the root locus method, angle condition and magnitude condition, I can determine the roots of higher order polynomial equations quickly. So this is a one more advantage of angle condition and magnitude condition of root locus. With this very brief introduction to this root locus technique, I am concluding this introductory lecture. From next lecture, let me solve problems on root locus. That's all from this lecture. Thank you all.